we left off looking at what the problems with continental drift were, and then I said that we're going to take a look at what happened after the Second World War to change people's ideas about the hypothesis of continental drift. So what were some of those changes? Well, we have to take a look at something known as paleomagnetism. So again, we see that prefix paleo, ancient, magnetism. So this is the study of ancient magnetic fields. And you might be thinking, how can we study ancient magnetic fields? Well, it comes down to something called the Curie point. The Curie point is the temperature above which a mineral loses its magnetic properties. And that also then means it's the temperature below which it gains its magnetic properties. And remember that the inclination and declination of the magnetic field varies depending where you are on Earth's surface. So let's say we have, we have our planet at time number 1 over here, and we have a continent sitting here, and a lava flow comes out on that continent. Well, lots of different lavas have magnetic minerals in them. And so this lava erupts, and it starts cooling down, and eventually it's going to cool below the Curie point, which is, for a lot of minerals, somewhere around like 580 degrees Celsius, something like that. So in any case, this lava flow, once it cools below the Curie temperature, all of those little magnetic minerals line up, pointing to the North Pole, right? So these guys are going to be pointing to the North Pole. Well, what happens if the continent moves? Well, let's say this continent ends up moving over to this location. My lava flow is still here, and those little magnetic minerals are still lined up. Once they drop below the Curie point, that orientation they're at is locked in place. So now they're going to be pointing off to a location that is not the North Pole. Okay, so that's something that can happen. All right, well, let's see what some studies then ended up happening in the 1950s. So in the 1950s, people discovered this thing that ended up being called apparent polar wandering. So first, starting in Europe, geologists studied these ancient magnetic fields trapped in those lava flows. And they looked at various ages, and they showed that the North Pole moved over time. So what happened? For example, we have a bunch of different lava flows here, and you can see their ages listed on there. And then we have also the inclination and declination right there. And so people then plotted the inclination and declination and figured out that, yes, today the North Pole is up here, but as we go back in time, right, the pole has kind of wandered around. And that was interesting. It was like, whoa, wait a minute. First of all, according to physics, the pole is supposed to stay somewhere near the geographic pole. It shouldn't be down towards the equator, so that was kind of weird. But it got even weirder. So they did these studies in Europe, but then thought, well, that's cool, let's do similar studies on different continents. And so they repeated these studies on some different continents, and then things got confusing. This is what happened. So they're like, all right, today the North Pole is here. 600 million years ago, the European North Pole was here, the North American North Pole was here, and the African was here. And it was like, wait a minute, how come the pole wandered in 3 different ways? You know, we can't have 3 North Poles. There can be only one. And so geologists got to thinking, and they're like, okay, how would this happen? And they figured out what I just showed you on the whiteboard, which is it wasn't the North Pole wandering around. The North Pole is pretty well fixed up towards the geographic rotation. It's the continents that are moving around the North Pole. And so it's just like what I showed you here. Those little minerals get locked in place pointing north. If the continent gets carried somewhere else, those minerals are going to be pointing in some direction that is not the North Pole. And that's why this is called apparent polar wandering. The North Pole isn't really moving all over the place. It just looks like it is. All right, so the conclusion then was the continents are moving, not the North Pole. Now, in actuality, the North Pole does move a little bit, but like I said, it always stays somewhere near the axis of rotation. It's not going to move to the equator. All right, so this was something that added even more evidence that continents are moving, like Wegener said that they were. And then comes another study. Okay, so the mid-ocean ridge system. Let me tell you a little bit about people's views of the oceans. If you would go back in time and think back into like the, 1700s, people thought that the world's oceans were kind of like a bathtub. You drop off the continent and there's this vast area where there's nothing, it just holds water. But in the 1870s, Britain sent a research vessel out called the HMS Challenger that was supposed to survey the ocean basins. They'd sail all over the place and they would measure the ocean depth and stuff, and they figured out that it's not this featureless area. There's an entire topography under the world's oceans. There's mountains and valleys and canyons and all kinds of stuff that we just don't see because it's underwater. And one of the things that was discovered is this thing called the mid-ocean ridge system. Now, the mid-ocean ridge system is this long, continuous mountain range under the oceans. And let me draw a cross-section of what this looks like. Okay. We all know my drawing abilities are just so awesome. And let's put sea level on here. Okay. So if we were to look at a cross-section, a side view of the mid-ocean ridge system, we have sea level all the way up here, and we have the mid-ocean ridge system. It's a mountain, right? So it's elevated here, and it's lower there, right? We're going uphill and then downhill over here. And usually at the middle of the mid-ocean ridge system, there's a little valley there. We're going to talk a little bit more about that valley later in the lecture. And in the 1950s, people studied the paleomagnetism of the rocks of the ocean floor. Just remember, ocean crust is basalt, which is lava basically, and I told you lava has lots of nice magnetic minerals in it, and so you can study the paleomagnetism. And they discovered something absolutely fascinating. They discovered that if we looked at the magnetism of the mid-ocean ridge, there were areas where the magnetism was normal, meaning all the little magnetic minerals are pointing north, and there were places where the magnetism was reversed, meaning all those little magnetic minerals are pointing to the south. Right? So that was discovered. So that's what we're trying to show here. I know it's a really crude drawing, but basically in the black, we're saying that's normal polarity, meaning pointing to the north, and in the white, that's reverse, where all little minerals are pointing to the south. So first of all, that alone was a neat thing to discover, right? Because that showed us that the magnetic field does reverse sometimes. But another thing that was discovered, notice that if we would cut the mid-ocean ridge in half, right, if we cut it in half, one side is the mirror image of the other, right? There's a pattern. And for geologists, when you see a pattern in nature, you want to know why does that pattern exist? Why do we have exactly the same, right? We have this normal, then we have this short reversed, a long normal, a long reversed, a short normal. Why do we have that same exact pattern on the other side of the mid-ocean ridge? Well, scientists started thinking about that. And in 1962, Harry Hess proposed this idea of seafloor spreading. And what he said occurred in seafloor spreading, he said that the mid-ocean ridge is not just a mountain range, it's a volcanic mountain range. And what's happening is lava is rising here, right in the middle. It's cooling, becoming solid, and then more lava will rise and kind of push the older stuff to the side. So basically new stuff's forming here and the older stuff's getting pushed to the sides of that mid-ocean ridge. That's what Harry Hess is saying. So basically the sea floor is spreading apart at those mid-ocean ridges. Okay, well, that sounds like a good idea. And this is his vision of it, right? At time 1, we have this eruption that's normal polarity, but then the magnetic field reverses, and so you have the lava that's reversed, and then some more that's normal, and that's why you have this pattern. That was his explanation for that. But if this is happening, that we have new sea floor forming at the mid-ocean ridge and the older moving away, we should have a very distinctive age pattern of the rocks on the sea floor. Right? The youngest should be right at the mid-ocean ridge because that's the stuff that's forming right now, and the older stuff, it should be getting progressively older and older and older and older as we move away from the mid-ocean ridge. It should look like that if Harry Hess is right. And lo and behold, after we started doing studies of the age of the ocean crust, that's exactly the age that we see. The youngest ages are these in red, the oldest are these in like dark purple. And so you can see at all of these mid-ocean ridges, that's where the youngest stuff is. And as we move away from those mid-ocean ridges, it gets progressively older and older and older. And so this is an important thing. We can see that this sea floor is constantly being created. But if we have new ocean crust being created at the mid-ocean ridges and the older stuff being forced away, that older ocean crust has to go away somewhere. If it didn't go away, Earth would just be getting bigger and bigger and bigger. And where does it go away? It goes away at a subduction zone. Subduction is the process in which an ocean plate sinks into the asthenosphere under another plate. And this happens because, first of all, that asthenosphere is squishy, so things can sink into it. And secondly, ocean plates are dense. Remember that from the last lecture? I said an ocean plate is denser than a continental plate or continental crust. And since it is denser, it's heavier basically, it can sink into the asthenosphere. Now, how this was discovered, we have to, again, we're scientists. We have to have evidence that this stuff is actually happening. And how this was discovered was through earthquakes. There were two scientists working independently. There's a guy named Wadati, who was working in Japan, and another one named Benioff, who was working in the United States. And they were both looking at patterns in earthquakes. And they noticed that in certain places, the earthquakes were like really shallow, close I'll use an example from like Washington State. You know, you have the west coast there with the Pacific Ocean. These guys noticed that like near the ocean, the earthquakes that happened were really, really shallow. But as you work your way eastward across Washington, the earthquakes would get deeper and deeper and deeper. Again, when scientists start seeing patterns, they start thinking like, why is this pattern there? What's going on to create that? So their idea of what was happening, they thought that these earthquakes showed where subduction is occurring. So let's use the example of Washington State. So let's say this is Washington State, and let's say that out here, right, this is the Pacific Ocean. I'm doing my best here, guys. And so we have ocean crust out here. Remember, it's a lot thinner than continental crust. And they said that underneath Washington, this ocean crust is sinking. Now, why do you get that pattern of earthquakes that are shallow here and deeper here? It's because those earthquakes are actually happening in the subducting plate. So as this plate is sinking into the asthenosphere, it's creating earthquakes along it, and the plate is very shallow here, so the earthquakes are very shallow, and the plate is much deeper here, so the earthquakes are much deeper there. And so that ends up this zone of these earthquakes that are getting deeper and deeper into the earth, and they get to about 660 kilometers deep, not much deeper than that. That area is called the Wadati-Benioff zone after the people who discovered it. And why this Wadati-Benioff zone is so important is because it marks exactly where subduction is occurring. Hey, C-3PO fell over. All right, so another example of that, let's take a look at South America. We have subduction going on there as well. We have the South American plate, we have the Nazca plate. Here in red, we have shallow earthquakes, we've kind of medium depth earthquakes in blue and deep ones in yellow. And notice lots of red earthquakes there. We get kind of those medium ones here, the deeper ones there, and they are showing us exactly where that subducting plate is located. So now we have new ocean crust created at the mid-ocean ridges, moving away from the ridges, and then disappearing in these subduction zones. Basically, Earth has this big conveyor belt, this recycling system of the ocean crust. All right, another thing that shows us that plates are moving around the planet, these things called mantle plumes. Now, mantle plumes, you sometimes hear them called hotspots, right, if you watch like Discovery Channel and stuff. And what a mantle plume is, it's a column of extra heat rising through the mantle. These things start at the core mantle boundary, and a column is basically like this. It's this narrow, small area of this extra heat rising up, and then when it hits the crust, it's extra heat, it's going to start melting things, and it's going to end up creating volcanoes. Now, the neat thing about mantle plumes is they are stationary. So the mantle plume is stationary, but the plate moves over top of it. And we can see that, for example, at the Hawaiian Islands. The Hawaiian Islands, the volcanism there, is caused by a mantle plume that is underneath them. And the Hawaiian Islands, in fact, are part of a much larger island and seamount chain. Now, what a seamount is, it's basically an underwater mountain, usually volcanic. And this chain, we can see Hawaii is there, and this Hawaii Emperor Seamount chain goes all over here. So it's a very long chain of islands. And when we look at the ages of these, we can see today there's activity, or the volcanoes that are that can erupt are on the Big Island right there. but as we look at the ages of the volcanic activity, they get older and older and older as we move over this way. And that's because the plate has been moving over that hotspot. So 64.7 million years ago, this spot was located over the Mantle plume. And over the past 64.7 million years, the plate has moved from the Mantle plume to that location. So these hotspots are great at showing us not only like how fast the plate is moving, because we can figure out how fast it's moving looking at those ages and how far they've moved away from the Mantle plume that created them. They can also show us the direction of plate motion. And the way you can figure that out is stand on the youngest island or the youngest volcano created by that Mantle plume and look towards the older ones. And that tells you the direction the plate is moving. Like right here, this spot, midway, was sitting on top of the Mantle plume 27.7 million years ago. Here's the current volcanism, and that tells us the plate is moving in that direction. But notice how these islands are moving or look in a different direction, right? 42.4, 64.7. If we look towards the older ones, that tells us the Pacific plate was moving in a different direction when this series of islands was created. So these hotspots are kind of neat because they can show us how fast a plate is moving. They can also show us the direction a plate is moving because they are stationary. And they can also show that over time, sometimes plates change the direction in which they're moving.